Hey Math 30-2s, how's it going? So today we are going to do modeling data using logarithmic functions and regression again. So you can see we have a bunch of tables of data. So we're only going to do two examples here. You guys know how to regress pretty well, so I'm just going to go over some of it with the calculator here and with Desmos, so you can see both again. Just a few things about this is that we always use, for some reason, logarithmic regressions to do our or natural log, sorry, to do our regressions. Just remember that a natural log is just like a log with a base e. So ln here, that's our natural log. That's the same as saying log with a base e. So if I go second 5, my base number down here is going to be the e, which is just right above the ln there. So second that. So that would be the same as a natural log. Like I think I showed this before, like natural log of 5 and the natural log of 5, they are the same thing. It's just a shortcut. We use natural logs a lot when we talk about calculus, and like I said, real world regressions are most likely, you can see here that they've mentioned here, a plus b ln x. They want that kind of regression. Okay, most of the time they tell you what kind of regression it is. Like since we are in the logarithmic regression, we're going to use logarithms. Now just watch out. One of the questions on the quiz mentioned that you should switch your x and y's because you can graph these exponentially too, with the height and the years on opposite sides, or we can graph them using logs by switching their x and y's. Remember we talked about that. Exponentials and logs are just when they switch the x and y's. So I can use either one, depending which side my x and y's happen to be on. Okay. So let's graph this. Use a graphing calculator to plot this data. So I'm going to go plot this data. I'm going to reset my tables. So I'm going to go number 4 here, clear all lists under mem. So second plus, and then go number 4. Perfect. Okay. So when I go stat edit, my tables are cleared. Now these are all messed up, like L1, L2 are not here. Try scrolling over to this side because maybe you see this instead. You want to make sure you enter your data into L1, L2. Okay, so I'm going to plot 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, 12 years of data here. 2, 4.8, 6.4, 9.5, 12. Oh, that's not 12, 13, 15.2, 16.6. I'm at 7, right? Yeah. Just making sure my data lines up. Hopefully by the time I get to the bottom, everything lines up. Yeah, got my data. So if they don't line up here, you probably missed a data point. You'll have to go back and try to find it. Okay, so I'm going to zoom. Actually, first of all, I'm going to clear out the things my y is equal to, turn on the plot if it's not turned on already, so hit enter. So my data's there. And then I'm going to go zoom. Oh, I got to find it. Zoom stat. I want to see what this data looks like. Zoom number 9. Ah, there we go. Okay, so it's going up and then it kind of goes down a little bit. I've got some weird data points here. I just want to double check to make sure I typed them in correctly. 2, 4.8, 6.4, 9.5, 13. Yeah, it looks pretty good. So my graph here, it's going up, coming down. Okay, is the average height increasing or decreasing? So the amount it's increasing is changing by smaller amounts, but it technically is an increasing graph. So I know that my a value, or the number that's in front of the log, is going to be a positive number. Remember, that's how we determine that. If it's negative, it's going the other direction. So I could show you what that looks like on Desmos here, just really quickly. I had a y is equal to, and I'm just going to put a BL in here. So that's what a positive b value looks like. That's in front of the ln. If it's negative, it's going this way, right? So I know it's positive, so it's going in that direction. That looks pretty similar to that kind of graph right now. So, okay, I would say this is a logarithmic graph. What kind of shape do you? So this is a logarithmic. Okay, so I'm definitely going to use a natural logarithm to do this. What is the approximate domain and range of this situation, though? Now, remember that the range of this graph is YER. Remember, that's like the abstract range. And my domain is everything greater than 0. So start at 0, then go in that direction. Sorry. So that's the abstract. But for this question, my domain, well, my domain makes sense. It's going to be, we don't have a label for that, but let's just call it X for now. Okay. It's got to be greater than 0, right? Can't be a negative age of tree. It doesn't make any sense. But my range is not going to be YER like I expected it would be. Like that graph is a YER graph. So this is a YER graph. Like Y is an element of all the real numbers. But it wouldn't make sense to have a negative height. So my height has to be greater than 0 for this to be true. Okay, what's the regression of this? So we are going to go stat, edit, not stat over to calc, sorry. And then we're going to find lnreg. I don't think we have any other log. What's in here? No. lnreg, so it's number 9 there. Okay. No. Enter, enter, enter. So I'm going to put here where it says store reg equation. Remember, we can go alpha trace, pull up y is equal to 1, and then calculate. So they put in the form a plus b ln x, just like what it states later on too. So it's in this form. Okay, so my b value is positive, which is nice. Okay, so that's good. We knew our b value is going to be positive, but we need, how many decimal places should I have? Negative 0.068. Let's go 3 decimal places. We seemed to work before in a previous question. There's my equation that we're going to use. Now I'm going to hit the graph button and see what that matches pretty closely. Some data points are a little bit off, but that's fine. Regression doesn't always have to match perfectly. Okay, so now we're going to use our regression here. I can use my graph, I can use my equation. What is the average height of the tree at 2.5 years? Okay. So what I'm going to do, average height, that's at 2.5 years. Years is my X, all right, and height is my Y. So we're looking for the Y when my X is equal to 2.5 years of age. So I can put that in the equation and go y is equal to negative 0.068 plus 8.316 natural log of 2.5. Okay, so let's try that out. I'm going to do it by the graph as well. The graph will give us a little bit more precise answers because I'm not rounding. I'm going to do it both ways. Why not? 1, 3, 6. That's not a 1. That's an ln. ln 2.5. Cool. Okay. So I get 7.3. How many to the nearest tenth of a foot? 7.4 feet. Okay. Let's go back to the graph here and double check that. So I'm going to go trace, because remember, trace, you're allowed to change your X values. Now I want to change it, but it's at the top there, it says P1, L1, 2. You want to hit the down arrow until it says the equation of the graph. You get all these decimal places here. And then I'm going to hit whatever X value I want. So 2.5. Enter. You can see there, it gets 7.4 as well. So that's perfect. Okay. What is the predicted average height of the trees at 20 years of age? So I could do the same thing. I put a little 20 there, but I just want to know when X is 20, Y, my height. So problem is this, probably if I go trace 20, it's not going to work. Now, why doesn't it work? Well, it doesn't work because my window doesn't go that far, right? The answer's got to be within the domain that they give you. It doesn't matter about the height. Maybe I can't see the top and bottom of the graph, but I got to at least have the domain. And x is 20, so that means I have to have the x max to be at least 20. I'm going to go 25. So there's the graph. Okay, I may not see 2020 is here. I may not see the graph, but it's within the domain, so I should be able to go trace 20. Okay, so it ends up being 24.3 feet. Now, is this realistic? Maybe. Usually when trees get a little bit tall, they stop growing altogether. They don't get any taller, right? It depends on the type of tree. Right? Maybe the tree dies, right? Who knows? Let's do this next one. According to your model, if the average height is 17, what is the age of this tree? So let's go to here. I want to know when, if y is equal to 17 feet, what is x? So the equation is going to look like this. It's going to be 17 is equal to 0.068 plus 8.316 ln x. I'm looking for x there. So I could rearrange this equation, solve for this equation, but why would I? I'm going to graph the right side, graph the left side. Sorry, right and left there, mix them up. So I'm going to put a 17. I already got the equation in my graph and calculator right here. Put a 17 there, hit graph. Well, that's nice. The line is right there. So I'm just going to go second trace, intersect, enter, enter, enter. So I get an x value of 8.1 to what? To the nearest tenth of a year again? So 8.1 years old. Perfect. Okay, so our last question here, last question of the year until we get to the quiz and the test, last lesson here. I'm going to use Desmos this time to do this question. So I'm just going to close this down. Go over here. I'm going to pull out my logarithmic regression. So I've shared this with you in Google Classroom here. Put my face down here. And I'm just going to type these in. So I got 100, 200, 400, 800. I don't think I had to switch this around. I just double check to see if this matches nicely here. Oh, my R squared is 1, so okay, it worked out really well. Let's just kind of zoom here. I'm gonna hold down Shift, zoom a little bit until I get my graph. At least I want to see my data points. Maybe you hold down Shift on the axes. Oh, there they are right there. Looking pretty good. Yeah, fits perfectly. So it fits perfectly. Here's my A and my B value at the bottom here. So my equation is going to be, so near 10th, okay, near 10th. So my A value is going to be negative 28.2 plus, because my B value is positive, 7.2 natural log of x. You notice I draw my L's there. It looks like that so they don't get confused. I'll probably go up here and do the same thing. These should draw them like a little bit more cursive like so they don't get confused as ones. Surprised I didn't draw that originally like that. That's fine. Okay, based on the regression equation, what is the minimum perceivable difference for a 21, I don't even know what the question talks about. Let's talk about this. An object of different mass are compared without a scale. To perceive the difference, the mass must be large enough. The difference in the mass must be large enough. For example, if you held in your hands mass between 5 and 100 grams, 5 grams, 100 grams, they will seem to be the same. Okay, 100 grams is pretty small, 5 grams is pretty small, so they'll probably feel about the same. A 5-gram difference is known as the minimum perceivable difference. Okay. For heavier objects, the minimum difference increases, the minimum Perceivable difference for the variable, yeah, okay. So as you get heavier and heavier, the bigger the difference doesn't really matter, okay? So what is the minimum perceivable difference for a 2100 grams? So that's beyond our domain. Remember, this is our x here. This is my y. So my x is going to be 2100 grams. What is my minimum perceivable difference? So I can put it in my equation, or I can go over here to my graph and find 2100 right there, right? So I can see here 26.962. As soon as I let go, it's gone, right? So I can put in here, because I want x to be 2100, I can put x equal to 2100, and there's my intersection point. So my y value is 20, and just do the nearest whole gram, so 27 grams. There we go. Not too bad. That's a pretty easy question. That ends off this year. Hopefully you guys did. Hopefully you guys enjoyed this. And I'll see you in some of the solution videos and quizzes. And if you drop by the Google Meet to ask some questions, that'd be great too. And if I don't see you, have a great summer. See ya.